This video will be a little recap of how the blue table works that was introduced yesterday in class, and the things you need to know by memory and the things you need to be able to do by reading the table correctly. Okay, first thing I want to come to your head is that there are many ions that you should never have to look up on the blue table because they are very distinct and they come from the periodic table. Their charges are always the same. So any element from group number 1, for example, is going to always have a 1 plus charge. And we learned why that was because it loses an electron to go back and become like the nearest noble gas. So this really should serve no purpose for you to go to that blue table to know the charge of sodium is a 1 plus. Now the name of a sodium, we learned because it's a cation, it never changes its ending. So another one, for example, say magnesium. Magnesium's in group 2, it's going to have a 2 plus charge. That ending also never changes. And the charge will never change. Magnesium's in group 2, it has a 2 plus charge. There are some nonmetals on the right-hand side that also have very distinct charges. So for example, chlorine in group number 17, when it becomes an ion, becomes a chloride. So the name of that ending is IDE, chloride ion. I will probably hit you with a rocket if you go to that blue table to look up the charge of chloride. Just like sulfide should be able to be predictable based on the fact that it's in group 16. It has a 2 negative charge. Now that's located on the blue table in the bottom half of the top table where all the anions are. They're there for checking, but they shouldn't be checked very often. You should know those. For example, nitrogen as an ion, being that it's in group 15, should be a nitride, and you should be able to go to your periodic table and predict that with great confidence. Those charges don't change. They are what they are based on the position in the table. Now it all goes to hell in a handbasket when we start looking at the metals located to the left of the staircase and in the middle of the table and the transition elements. Those metals can have more than one charge. And if a metal can have more than one charge, it is called a multivalent metal. Now multivalent metals, the periodic table doesn't help us that much because the predictions are not as predictable, for lack of a better description. So, for example, you should know soon, based on the information in our booklet on page 5, that there are 2 forms of iron, and they are iron 2 and iron 3. The name of those ions can change whether or not you're using the classic name or the stock name. I expect you to know both. So what the blue table will help you with is it will show you that there are 2 forms of iron, and it's your job to know how to name them both ways. If you were using the stock name, then the Roman numeral simply matches the charge. So an iron 2 iron would be the first one, and an iron 3 iron would be the second one. That's simple because it matches very distinctly to the charge. The classic name is the older system, but it's still in use. Your job is to know the prefix for iron. You should know that it is Fe, and that, of course, is very similar to the chemical symbol. The ending will depend on which iron you're talking about. Because iron comes in a 2 and a 3 combination, the lower charge, it has an OUS ending, and the higher charge has an IC ending. So a ferrous ion is an iron 2, where a ferric ion is iron 3. Your job to know the Aus is lower, the IC is higher. Let's have a look at the ion sheet that you have. I'm going to just randomly talk about some stuff. So for example, in the 1 plus column, I see there's a copper 1 ion. In the 2 plus column, alphabetically, I see there's a copper 2 ion. So by having this table in front of me, I would be able to know the copper 1 would be the cuprous, and the copper 2 is the cupric. The lower is the aus, the higher is the ic. Your job is to know what the prefix is for copper. For example, I can go to the table and I can find iron 2, and I can find iron 3. I could find chromium 2 and chromium 3. I could find cobalt 2 and cobalt 3. So it would be cobaltus, cobaltic, chromis, chromic. The ending changes. The lower is the aus, the higher is the ic. There's another couple ones that are quite common. The 2 and the 4 pair. What I mean by that is tin, for example, tin 2 and tin 4. And also lead 2 and lead 4. If you go to your periodic table and you look and see what column the tin and the lead are in, you will note it's group 14. And it kind of makes sense in a way, where it's group 14 and it could lose 4 and become a 4 plus. Not completely off the realm of possibilities there. Something to note, for manganese pair, there's a manganese 2, which is located on the table quite nicely here, but there's no manganese 3 over here. Your job is to write it in, and it's your job to memorize it, because it's not on the table. So Mn 3 plus needs to be added to your table. You will also notice that there's no gold. From your page 5, there is such a thing as a gold 1, and there's a gold 3. Or-is is the lower. That's the or-is. And gold 3 is auric. So they need to be locked into your noggin. Something else to help you get through some of the difficult times ahead. There's a lot of extra ions on here that we will very rarely ever use. So don't be too overwhelmed by that. Something that will come up quite a bit, however, is the fact that some metals in the transition part of the table don't have more than one charge. So look at silver. Silver, you'll notice, has no Roman numeral beside it. By finding silver in the 1 plus column, that tells me with great confidence, since there is no Roman numeral beside it, there's only ever one form of silver. It's not a multivalent metal. Zinc as well is only ever going to be a 2 plus. Cadmium up here has no Roman numeral, so it's only ever going to be a 2 plus. Same thing if you have a bit of a brain fart later and you're looking around and trying to think. Maybe you will notice that sodium never has a Roman numeral beside it because sodium can never have more than one charge. Aluminum can never have more than one charge. You cannot start putting Roman numerals everywhere you see them. Only elements that can have more than one charge should have a Roman numeral. Something else to notice, to prevent the question coming up later, is nickel. On this table, there's only one nickel, but it has a Roman numeral, because technically there is a nickel 3, but it's very, very rare. So you should include the nickel with the 2 after it, because it's quite common, but it's not always compared to nickel 3. Something else to think about. The anions here at the bottom, they are all listed very predictably based on the periodic table. So the halogens, 1 minuses, oxide, selenide, sulfide, etc., the 2 negatives. The one weird thing about this table that you probably need to hear the words about is mercury. Now mercury is an odd bird. Mercury is located in the 2 plus column. Mercury 2, the mercury 2 ion is the normal mercury ion. There's nothing odd about that one. It's just simply Hg2+. Now, because there's another form of mercury, there will be an ending that will go along with that. The other ion for mercury is actually located in the lower right-hand corner of your blue table, way down here. And mercury is a weird bird. Mercury is the only ion that can have a subscript built in its single state. Mercury 1 is actually a mercury with a 1 plus charge and another mercury with a 1 plus charge, where each of those atoms has lost an electron, and they actually stick together. And you get 2 mercury atoms together with a total net loss of 2 plus. And that's called the mercury 1 ion. It is the only ion where the Roman numeral does not match the charge. The Roman numeral 1 doesn't match the charge of a 2 plus. That's the weird bird, so you know you're going to see it a lot. Something I want you to keep in mind when you go to sleep at night, having your nightmares, is this 2 at the bottom never gets manipulated, touched, changed, or tweaked in any way. When a mercury 1 ion goes into a compound, you can't touch that 2. So I've often said before, no touchy the 2. A mercury 1 ion has a 2 built in that you can't change. I'm going to do one example because I did a few in class on Friday. I'm going to take a compound, just a random compound off the top of my head. I'm going to do calcium nitride. If I look at that compound, I see a metal and I see a non-metal. That should scream at me that that's going to be an ionic compound. And ionic compounds are written chemical formula-wise by balancing the charges of the individual ions. Calcium has a charge of a 2 plus based on the position in column 2 in the periodic table. Nitrogen has a charge of a 3 minus. What that means is calcium is going to lose 2, but nitrogen is going to gain 3. Well, those aren't equal, and everything in chemistry has to be balanced. So what has to happen, I'm going to show you this. I didn't do this on Friday, so those of you that are watching this will get an advantage. Okay, calcium has 2 valence. Nitrogen has 5. I do that in different color. Nitrogen has 5. So if I draw nitrogen with its 5 valence, everybody wants to have 8. There are 3 that are unhappy. 2 nice pairs. So what happens is calcium loses. So it loses 1 over here, and it loses 1 over here. Well, now we have 2 over there. So now we have an extra dot here, and we have an extra 1 here. And those are now gone. Well, that's great, but nitrogen still needs another. So a second calcium will come along, and it'll donate another. Well, now nitrogen is fully bonded up, fully happy, but I have an extra calcium electron. So that's no good. I need another nitrogen. So I have another nitrogen. Donation, loss of electrons, comes over, pairs up there. Well, that's great, but I still have 2 empties. So I now need 1 more calcium to finish making everybody happy. So that donates 1, and that donates 1. And now we have everybody, calcium, each of those calciums lost 2. So 6 electrons were lost, and those 2 nitrogens, 6 electrons were gained, and everybody's happy. To show that, what you have to do in a chemical formula is a method called the crisscross system. So the charge of the nitrogen, not the charge, just the number, will come down. and become a subscript, and the 2 will come down here and become a subscript of nitrogen. What that really means is to balance calcium nitride, we need 3 calcium ions and 2 nitride ions to get a grand total of 6 positive. If I put the charges in there, that might help for the original. That would give me 6 pluses and 6 minuses, and that's neutral. Your final answer can never have the charges in it. So for one balanced ionic compound of calcium nitride, you would need a ratio of 3 cations, 3 calciums, for every 2 nitrogens to make it balanced. Say we had another example where we were told we have a compound containing chromium 2 with, let's say, bromide. I look at that name and I see metal, non-metal, so I know it's ionic. I see chromium and bromine, that's only 2 elements, so it's binary. To write the chemical formula, I write the formula of each of the ions. Chromium 2, the fact that it's a stock number, tells me that right away that the charge is a 2+. Bromide, being that it's in group 17, has a 1- charge. Well, that compound is not balanced as is. So you can do the whole find the common denominator, or you can do the balancing of the charges with the crisscross method. So I need 1 chromium ion to go together with 2 bromide ions to get a neutral overall compound. Because a 2+ ion balancing with 2 1- ions would give you a 2- and a 2+ opposite from each other. And that is balanced. So your final answer should be CrBr2. And no charges should ever be located in your final compound. That's chromium 2 bromide. That is what we call a binary ionic compound because it contains only 2 elements. I'll do one more. This time I'll use the classic ending. Say we had stannous sulfide. So your job is to say, oh, it's an OUS ending. That means it's lower of the 2 possibilities. The prefix stan, you need to know that by Tuesday, that is tin. So you go to your blue table if you have to. If you haven't got it memorized, which you should have it memorized for Tuesday. Stannous, tin can come in either a 2 or a 4. Because it's the lower, it's the tin 2. So stannous is the same thing for SN. Sulfide is sulfur in its ionic state. It's an anion, it would lose 2. The purpose of crisscrossing is to balance the charges. Well, we don't have to crisscross. And in fact, if we did, we'd be wrong, because that would give us the same number. It would be unnecessary. This compound is actually balanced. So the final answer should simply be SNS, tin sulfide. Tin 2 sulfide is that's the other name. Don't have to do that, but I'm going to. Tin 2 sulfide is the other name for that compound. The purpose of crisscrossing is to balance the charges. They're already balanced, therefore the compound is neutral. 1 tin 2 ion and 1 sulfide ion would balance that compound. Hope this helps. What I'd like you to do for the weekend is to get into your head as much as possible. Iron comes in a 2 and a 3 pair, so it's ferrous, ferric. Cobalt comes in a 2 and a 3. Copper comes in a 1 and a 2. Tin and lead come in a 2 and a 4. Gold comes a 1 and a 3. And mercury is a weird bird. The weird bird is Mercury 1. It's actually Hg2 with a 2 plus charge. Little quizzy on Tuesday. First thing, 10 minutes only maximum. Fast, fast. Have a nice turkey weekend.